the pressure, specific volume, temperature, behavior of low and moderate density gases. One form of energy possessed by a system discussed in section 2.6 before is intermolecular potential energy. That energy associated with the force between molecules. Associated between it was stated there that at very low densities the average distance between molecules is so large that intermolecular potential energy may effectively be neglected for the very low densities. The intermolecular energy, potential energy, let me the distance between, because of the large distance between molecules. In this case, the particle would be independent of another, a situation referred to as an ideal gas. For the very low densities, the large distance between molecules, we have the assumption ideal gas. Under this approximation, it has been observed approximately that experimentally that to a close approximation, a very low density gas behaves according to the ideal gas equation of a state. A state which expressed as or for the specific volume we have R bar T, which N is the number of kilomoles of the gas. Kilomole of the gas. So we have this expression for N R is the universal gas constant, R bar. It is a standard universal gas constant or kilojoule kilomole Kelvin. And T is the absolute temperature in Kelvin. Which we know is the T on centigrade plus It is important to note that T must always be the absolute temperature whenever it is being used to multiply or divide in an equation. The ideal gas absolute temperature scale will be discussed in more in detail in Chapter 7 in English Engineering System. We have R equals to on kilomole ranking absolute temperature in this system of units. Substituting to the previous temperature, we find that the ideal gas of a state can be written conventionally in the form PVMRT or a RT. In this case, R equals to R bar on the molecular mass of the substance. In this case, R is different constant for each particular gas. The value of R for a non-bearer gases in the table are listed in table A5. Because of its simplicity, the ideal gas equation of states is very convenient to use in thermodynamic calculation. However, two questions are now appropriate. The ideal gas equation of states is good approximation at low density, but continuous low density. So the main question is, the first main question is at what continuous low density the ideal gas approximation is good approximation for the low density, and the main question is at what continuous In other words, over what range of density will the ideal gas equation of a state hold with accuracy? The second question is, how much does an actual gas at a given pressure and temperature deviate from ideal gas behavior? And the second question is how much does the ideal gas and actual at a given pressure and temperature deviate from ideal gas behavior. So one question is about the continuity of the low density and the pressure and temperature limitation for the actual gas to behave an ideal gas. One specific example in response to those equations is shown in the picture here. One example shown in this picture, a TV diagram for the water that indicates the error is assuming ideal gas for saturated vapor and for the superheated vapor. As would be expected, at very low pressure or high temperature, the error is small. High temperature, this area. Temperature and also for the low pressure. For pressure, for example, this point, the pressure is below 10 kilopascal, and high temperature, for example, this point. Also, the specific value, as would be expected, at a very low pressure and high temperature, the error is small but becomes severe as the density increases. Becomes severe at density increase. These areas, low specific value and high density, the error becomes higher. The small general trend would be accurate in referring the previous pictures. As the states become further removed from the saturated region, the behavior of gas becomes closer to that of the ideal gas model. So the next section is the compressibility factor in the next video part.